Yeah, hello and welcome from my side as well to this session today about simplifying your thermal simulations with the Immersed Boundary Method. My name is Alexander Fischer. I'm a co-founder and product manager at SimScale, and I want to introduce you today to this method and show you why it's a great addition for potentially your thermal simulation tool stack. The agenda for today is simply a quick introduction to SimScale, the tool and platform, and specifically how we try to empower engineers across the globe. And then we will dive a bit into details about the Immersed Boundary Method itself and why it's such a great asset for thermal simulation, so what the benefits are. After that, I will show you a quick case study of an EV inverter liquid cooling case, and then show you the live platform for a few minutes based on an EV battery pack. So SimScale, the company, was founded about 10 years ago. We have people all around the world, but more importantly, we have a lot of users worldwide, paying customers, academic users, community users that contribute to the content that is done on the platform. And as you can see, we have many simulation projects and simulations going on each and every day. We've also been part before of the Charged EV's virtual conference. So if you're interested in some other topics like API-driven design optimization, different use cases that can be done on the platform, feel free to look for the on-demand sessions as well. Great. So how is SimScale empowering engineers? We are a cloud-native simulation platform. So that's the first important point. You can simply access this platform by typing simscale.com into the URL of your browser. You only need a standard web browser, a stable internet connection, but there's no requirements for hardware. You don't need to install anything. You can essentially just create an account and directly start. We have broad physics range on the platform, so it's not that you would be using a different tool for different simulation setups, and if you then kind of hit the limits or boundaries of one of these tools, you need to learn a new tool. No, it's the same user interface for all of the different physics, and you can use it and simulate and share with your colleagues. That's also an important point, the sharing, so the collaboration and support. It allows us as a platform simply that projects can be shared among users, among teams, that you can work together on a project, but also that we as a support team that is available to you can look into your projects when you share it with us and help you if you have any problems, etc. So that is, we're quite proud of that. So it's a great asset. I believe you don't need to create a support ticket or anything and wait for a reply. You can directly interact with our support team. And you can really use the power of the cloud on any scale. So you can run simulations to validate or verify just one design, but you can also run parameter studies, tens, hundreds of simulations, basically unlimited amounts. If you want to train a model, or if you want to create a simulation set that you want to derive parameters from for reduced order modeling or similar. And you can run SimScale quite cost effective. So you can just start with one account, but you can also roll it out to an entire organization on a reasonable price. Great. So I mentioned the broad range of physics that is mostly a flow, so kind of like a pressure drop in this electric motor, for example, but you can also look for the thermal results. You can run conduction only or convection, conduction and radiation coupled in a simulation and really look at maximum temperatures, operating conditions. You can look into structural simulations, nonlinear behavior, vibration analysis. So like, for example, if there is the rotational range of this electric motor is within range of some of the eigenfrequencies. So if you would have problems around this, and brand new also some electromagnetic simulations, so electromagnetic fields, forces, etc. can be analyzed. So if you're a designer of components, you want to look into some of these fields, you can do this all via the same user interface on the same model. You can also use SimScale to do excessive design iteration. So in this case, on the inverter model, just changing the liquid cooling channel a bit. You can upload as many variants as you want, replace it in your simulation setup, and just hit start again. The assignments can be mapped. So that is basically no manual effort that you need to do here, but you get a lot of insights and can do informed decisions early in the design process. You can also use it to run 3D simulations, get the full result fields, but use these result fields, temperatures, etc., to derive some reduced order models or compact resistance models out of this. So you can get the heat transfer coefficient values, run different flow rates, different coolant temperatures, and get the values out of this and run a very fast transient 1D model based on that, if that's a requirement. Great. That was a quick introduction to SimScale, and now I want to speak a bit about the main topic today, about the Immersed Boundary Method and why it's such a great asset for thermal simulations. I want to start with the challenge that usually thermal simulations around electronics have. That is mostly that the CAD models usually are quite complex. So there's many parts in there. They might come from very different sources, downloaded from supplier web pages, created for parts that you manufacture yourself by a designer in-house or even by consultants. So you might have different tools, different CAD qualities that are combined into one big assembly, and where you have potentially tolerances, assembly gaps, etc., that might hurt your simulation. So as an engineer, what you need to do is now you either need to invest a huge amount of cells, so kind of meshing elements, to resolve these very detailed CAD models, if even possible from a quality standpoint, or you now need to invest a lot of time, either to simplify your model, so the CAD model, or to spend a lot of time in the meshing details to get to a reasonable amount. And in this case, if you didn't simplify the model, you still probably will have a problem that your mesh quality is quite bad, so that you need to then play with the numerics or still do some significant cleanup to get to even to a state where you can simulate the model. And that is really painful. So the most painful part about it is that you are actually spending times for geometrical details that are mostly insignificant for the thermal behavior, but are just required to be resolved so that you can even run a simulation. And this problem can be solved by using the Immersed Boundary Method, because this method does not resolve the geometry as it is in the CAD, so really in detail body fitted, but it actually immerses the geometry into a Cartesian background grid, as you can see here at the bottom. So you can still define how fine you want to go around the specific elements, but you don't need to resolve all of the little details that are not really important for your simulation down to the level of the geometrical detail. And that is really great. And you can run it all on essentially a perfect hex mesh, where you just have the transitions between the finest levels, but you have no skew problematic cells in there at all. And you don't care about topological details like logos, for example, at all. You just decide on how fine do you want to go around certain details. Of course, you can run just the default sizing to use the automatic meshing. And that enables you to run essentially, or invest the computing resources that you have to run what is really physically relevant and not focus on what is geometrically challenging. And all of that without spending all of the time and pain to do some cumbersome cleanup and simplification. So that is really great. Now, I want to show you this at the example of an inverter case, but first walk you again through why this is so great, or kind of what's the additional design space that you get via using this method. For that, I listed here on the x-axis, you have kind of our mesh fineness from very coarse to very fine, and you can see one important result component, for example, the maximum temperature of the battery cell. Now, I also plotted here a reference solution that might come from tests or from other sources. And I've listed here now simulations based on the original and simplified model for both methods. So the body fitted and the immersed boundary method. Now, for the body fitted method, we usually cannot even mesh or run the simulation on the original model. Either the mesh will be huge, or it might not be even meshable, or the simulation might diverge. So we're not even looking into this. For the simplified model, we can create a body fitted simulation. And we can see here that the finer we go, the closer our solution gets to the reference solution. So that is great. But we can only go to a certain level of coarseness. After that, really, the simulation will again fail, diverge, because we have bad quality elements in the mesh. That is different if we run the simulation on IBM. So in this case, also the simplified model. In this case, we can run the simulation with much coarser resolutions because we are not caring about these geometrical details. So we're just getting a bit coarser on the physically relevant parts. And at some point, obviously, our solution will become physically not so relevant anymore. So we're just going too coarse, but there's a reasonable range still that we can really use and run many simulations or test it. Even more importantly, it looks the exact same or almost the same for the original model, right? So because our mesh sizes are expected for similar finenesses to result in the same simulation setup or the same simulation that gets solved for both the simplified and original model, meaning we don't actually even need to do the simplification, and that is great. For very fine meshes, we would expect all of our simulations to get close to the reference result be very close in range. But what it really opens up is that we can run early in the design process without simplification and cleanup. We can already run simulations, and we can decide about the accuracy level that we want to apply. So in the inverter case, here we see a 12 MOSFET inverter with a liquid cooling channel where we want to see the max temperature and the liquid cooling channel drop. I did such a study. So what this means is I ran on the original model and on the simplified model both the CHT body fitted solver and the immersed boundary solver. And I listed here the temperature rise in the hottest MOSFET and checked essentially what's the diff to the to a reference solution, right? So what we can see here is that for the original model, we have for the default finest settings huge mesh sizes, way higher than 10 million cells, both for the original and simplified, a bit lower obviously for the simplified model. So that means for us that we need to apply a lot of computational resources and long turnaround times to run these simulations, unless we spend now quite some expertise and time to build coarser meshes, but by doing manual refinements, investing a lot into the sizing, etc. So that is better for the simulation runtime, but we spend more manual time. That is also not what we want. For the IBM solutions, though, we can run a broad range of finenesses, so we can go very coarse, and we can do so for the original and simplified model. So we can run this without any simplification, right? And we have the same mesh fineness for the same sizes. So for the original and simplified, fineness 5, so our default sizing, results in almost the same mesh size. Here, down to the level of precision, exactly the same mesh size. But we already have decent results. So compared to the reference solution of the CHT solver, we are within 5% or even lower. And that is quite decent if you want to do early design studies. Great. So let's look at this also on the live platform. For that, what I will do now is I will simply jump out of the slide deck here and will move over a second simulation tab. So as you can see, we are still looking here at our browser. So I'll quickly jump to my dashboard. So we have simscale.com. This is my dashboard. You can see all of my projects here that I can easily access. In this case, these are all public projects, so demo projects, etc. If you're working as a SimScale customer, obviously all of your content is confidential. You can decide exactly within your organization which teams, which users have access to what, right? And you can decide yourself if you want to share something with our support team if you need some help, for example. You can easily open up such a project by opening Workbench. I did so here already. So we can see here a loaded result of our battery pack. But I first want to give you some insights on what's a bit different for such a platform where you access your simulations via the browser. So you have here a little button that says share. Here you can now share your simulation project with colleagues, with customers, etc. And you can exactly define what's the permission level that you want to give. So should it be edit permissions or just watching the results with can view permissions? And you can decide if you want to share the project with our support. The same you can also do down here by opening up this chat window. So also here you can share the project with our support. And here you can now directly interact. So if you have a question, if you're stuck somewhere, or if you want to have our opinion on the simulation results here, you can just reach out to us, get an immediate response, and interact with our support team. Apart from that, the user interface might look familiar to someone who is used to running simulations. Here we are in the post-processing environment. I can now start here the animation of the flow field inside, for example, of this battery pack. So we have here a couple of cells in parallel and serial. We see the temperature field in this thermal scale, and we see the velocity here plotted on the streamlines of the flow field, and we can do now all sorts of post-processing, add cut plots, etc. So in our case, for example, I could quickly hide the particle trace and add a cutting plane if I want to do this, right? And then I can look, for example, in the interior of the model, check out maybe if I have recirculation zones, similar problems in my design, and look into these specifics, for example. So that is always possible. How I even get to such a simulation result is by first uploading my geometry. So I'll show you now how you get to such a result. Here we can see the original battery pack. So I'll quickly hide a few components in here. So we have here the flow domains and flow channels. And now you see the same components that we saw in the post-processing. We see here the bus bars, etc. And you can see that we have now a lot of details in here. If I zoom into this connector, you can see that there's many small faces and details that are really not relevant for the thermal behavior, but that are originally in the model. The second model that I loaded was this simplified battery pack. So we can see here that most of these details were now removed. So we manually cut this down to what is really thermally interesting. Running such a simulation means now that I just create a conical heat transfer analysis, either the body-fitted style or the IBM simulation. The setup is almost the same for both of them. So now, for example, for my original model with the IBM method, I need to just provide the different material properties. So for example, for the air, the aluminum and copper, I can define these material properties myself, or I can load it from the default library or from a library that I create for my company. And I need to define the boundary conditions like inlet and outlet conditions for the air domain in this case, and the power values. So here, for example, I can define the wattage. This is a 1C scenario, so I have about 20 ampere drain from the battery pack, and I have about 0.24 watt of power emitted by all of the battery cells. If I want to test now, for example, a design for different states, I can also make this a parametric value. So I can define here 0.24, 0.48, and maybe also 0.96 watt. apply this, and then I get a parametric value for this setting. And if I later on want to run my simulation, I just click on Start a new simulation run. The simulations now get carried out in the cloud. So I will run here an experiment. And I can see down here from the finished simulations that are already here that I now have a new experiment, and this experiment is running the different parametric values for the power source. So that makes it very efficient, can be also 10 or 100 simulations. Great. The last thing that I wanted to show you now is that for this original simulation, the setup is the same as for the body-fitted style. We already looked at the results in the post-processor. We can also look at, for example, some area average results that are plotted here over the iterations until the solution is fully converged. So this, for example, is now the result of the highest temperature cell, which is around 302 Kelvin, so 35 degree Celsius. 30 degrees Celsius, what we get roughly here. So that's our result, 302.8. If I run the same simulation with IBM now on my simplified model, I get almost exactly again the same mesh size, so 5.5 million, and my result will be 302.3. So I cannot even say, is this now because I simplified the model, or if it's because the solution of one is better or not, but it's really in close range, right? So we are talking about 0.5 degree difference here on that mesh size for such a complex model, meaning that for my design decisions, I'm probably already in range where I'm quite happy with such a result. And we can do the exact same for the body fitted one as well. So here we now, let me quickly show you the mesh in this case. We have here now a simulation with a body fitted mesh. So here we can see, looking into it, that we have here the geometry exactly resolved by tetrahedral elements, and that we have here also some boundary layers on the flow domain. And running this on a 6.9 million mesh leads for us to a result of 302.2. So again, we're really close to this, but we saved all of the time of the simplification, and we can run this quite easily. In this case, it's also not possible to go way below. So on 5 million, my simulation is already diverging. So that's why I probably should go finer in this case to run it. Great. So that is what I wanted to show you on the platform. I'll quickly jump back to our slides. So what I've shown you in the live demo simply is that the setup is very similar if you're running a body fitted or if you're running an IBM simulation. There are also great use cases for running body fitted simulations if you want to resolve, for example, flow channel details in a CFD analysis in very detail. But for the thermal behavior, running IBM analyses specifically early in the design process is very helpful and very easy. Great. So we hope that your application is next on SimScale. You learned today that it's quite easy to get started. So I hope you give it a try. Please feel free to reach out if you want to do that. And I want to thank you for your interest and attention.